I'm now going to explain how to find the length of a polar curve r equals f of theta, where theta goes from alpha to beta. I'll first write down the formula and then explain why it's true. So the formula is that the length, which I'll denote by L, is the integral from alpha to beta of the square root of r squared plus dr d theta squared d theta. And instead of dr d theta, you could instead put f prime of theta there. So why is this true? Well, first, the explanation in terms of vectors, and if you're not yet comfortable with vectors, ignore this, is as follows. So if we think of theta as representing time, then the length is the integral from alpha to beta of the length of the velocity vector d theta. And what does the velocity vector look like? Well, suppose we're at some point here, and through this point there's a circle of radius r. And the velocity vector can be decomposed into two components. So first there's a tangential component, which is tangential to the circle of radius r, and this component has length r. Because if you're moving along the circle of radius r, and if theta is increasing at unit speed, then you're moving at speed r. Then there's a perpendicular component, which tells you how fast are you moving away from the circle of radius r, that is, how fast is r increasing. The length of this component is of the velocity vector is dr d theta. The velocity vector is the sum of these two components, and the length of this, by the Pythagorean theorem, is the square root of r squared plus dr d theta squared. Okay, now if you don't like that explanation, then we could instead convert to Cartesian coordinates. So I could think of my curve as the parameterized curve x equals r of theta cosine theta, and y equals r of theta sine theta. And then the length is the integral from alpha to beta of the square root of dx d theta squared plus dy d theta squared d theta. So let's figure out what dx d theta squared plus dy d theta squared is. So dx d theta equals dr d theta times cosine theta minus r sine theta. dy d theta is dr d theta sine theta plus r cosine theta. So when I square these, I get dx d theta squared equals dr d theta squared cosine squared theta minus 2r dr d theta cosine theta sine theta plus r squared sine squared theta. And dy d theta squared is dr d theta squared sine squared theta plus 2r dr d theta sine theta cosine theta plus r squared cosine squared theta. So when I add these up, I get dx d theta squared plus dy d theta squared equals, so adding up these first terms here, since cosine squared plus sine squared equals 1, I get dr d theta squared. And adding up these two terms, well, they cancel. So let me cross them out with my red canceling pen. And so that's 0, and then the third pair of terms gives me r squared. So dx d theta squared plus dy d theta squared is actually equal to r squared plus dr d theta squared. So that proves that, so this formula gives this formula, which is what I wanted to prove. Let's do an example. Let's calculate the length of the curve r equals 2 sine theta. We know that the length is the integral of the square root of r squared plus dr d theta squared d theta. Now, what are the limits of integration? Well, by default, if they're not specified, then we would go from 0 to 2 pi. Okay, so we have the integral from 0 to pi of the square root. Now, r is 2 sine theta, so I square that. And dr d theta is 2 cosine theta, so I square that. So this is the integral from 0 to pi of the square root of what? Well, this is 4 sine square theta plus 4 cosine square theta, so that's just 4. And I always take the positive square root, so I have the integral from 0 to 2 pi of 2 d theta, which is 4 pi. Okay, is that correct? Well, let's look at the curve. What does this curve look like? So you'll recall that we sketched this curve, and in the process of sketching this curve, we converted it to Cartesian coordinates and discovered that it is a circle of radius 1 centered at the point 0, 1. Now, being a circle of radius 1, its length is 2 pi. But in this integral, I got 4 pi. So what's wrong? Well, the problem is I needed to think more carefully about the limits of integration. So as theta goes from 0 to pi, remember as theta goes from 0 to pi, we go once around the circle. This is where r is positive. And then as theta goes from pi to 2 pi, we go around the circle a second time. This is where r is negative. So if theta goes from 0 to 2 pi, I'm going around the curve twice, so I'm actually going to get twice the length of the curve. So to get the correct length, I should just integrate from 0 to pi. It would also be okay to integrate from pi to 2 pi. So let's fix this. And this would be 2 pi. And that's what we're supposed to get. So if you're calculating the length of something, you need to be careful that you are choosing your limits of integration to make sure that you are covering the whole curve exactly once. No more than once, no less than once.